right? This is what you will see. This is a die, and it is connected to the bond wires, and then this is typically how the pins are connected. So this is just to show how the die gets bonded onto your package. So one of the challenge here is also to understand how to do a validation. How do you test it in the lab? These are power management ICs, and how do you do them? So you can build a validation board, and what we did was, for the temperature characterization, we have put a socket which can withstand the high temperature, and only the device was put inside the socket, and everything, all the additional bells and whistles were all covered. So you can now use a thermal insulating rubber. The socket with the DUT is here, and all other external components are capacitors. So because the commercial components that are available, like the external Schottky or the inductor or the capacitor, they would not withstand 150 degrees centigrade. Right? These are withstanding only smaller temperatures, but your IC, you have to test it at 150. So now, if you put everything together and just blow hot air at 150 degrees centigrade, they will fail, obviously. And you don't know whether it is due to the component or whether this is the IC. The challenge here was to see how can we come up with a testing of IC at 150 degrees centigrade, still preserving the temperature, still limiting the temperature to these external components. An easy way is to use a thermal insulating rubber with some setup like this, where if you just cut, and then you can see that the device is all placed here inside the package, and this is a socket. You close it, you have a thermal insulating rubber, and put it below a thermal stream. This thermal stream will now regulate the 150 degrees centigrade temperature. The other interesting thing is, you can see that the components are all sorted on the back side of the board, back side of the PCB, the external components. Only the IC is susceptible to this thermal stream. With that, we were able to characterize. This is all the bench setup. You have GPIB cables, and this is the DUT, where you can connect the power supply, multimeter, oscilloscope, and thermostream. All can be controlled through a lab view in a PCB. So it's not, you're no longer doing a manual testing. You can now do a complete automated testing to do the lab, and we just use an FPGA to control the drivers here. So these are the efficiency curves. So you can see all the light lines. They are all without adaptive biasing, and all the bold currents are with the bold lines are with the adaptive biasing. You can see that the y-axis is efficiency. So as the load reduces, the efficiency is now improving for all the light load conditions. And this was done at 6 volts, 12 volts, 18 volts. And when you do a temperature sweep, you can see that while the conventional LDOs really had conventional systems had a severe problem at higher temperature, this adaptive system helps you to have much higher efficiencies, even as high as 150 degrees centigrade. And this was a work that was done literally 7-8 years back, and at that point, this was the first reported DC-DC plus LDO combination at 150 degrees centigrade, which was tested and reported. Okay, and this short summary of a conventional dropout versus an adaptive dropout. So for all light load conditions, the efficiency improves, so which is good for the overall system. And this was a comparison of existing DC-DC plus LDO circuits, and you can see that there are very few that had really reported at 150 degrees centigrade, and we were the ones who first reported it here. And this is a comparison of all the load regulation, system ripple, and the total efficiency that you see. This was with respect to the commercial products. We always do a benchmarking with respect to what is available in the market, and you can see that the efficiency and light load efficiency was also significantly higher with this type of a power management architecture. So the goal was to, this is my last slide, the goal was to design an integrated generic efficiency improvement solution that can work on existing hybrid regulator and something that can work until 150 degrees centigrade. And what we achieved was this IC, which is quite small, and that can be mounted and that can be tested until 150 degrees centigrade in automotive application. The key takeaways when you design PMICs: one, some of the device parasitics are not modeled. When you have more wells, these high voltage wells, some of them are not modeled, so you have to be very clear about the device modeling, understand which devices are getting turned on, worry about latch up, ESD, so on. Choose a process that has good noise, mismatch, and design rule guidelines for extraction. Layout is key to proper functionality of PMICs. So power converters, the analog layout is extremely important because the metal routing can really kill your performance. So there are also special tricks on how to do a metal routing for these huge power MOSFET transistors. And consider the self-heating effects to compute the simulation temperature. Thank you. And then my last slide. So we've, like I said, This is part of our EduTech initiative from MOSart Lab. So we have partnered with IIT Bhubaneswar, where we are running this professional diploma program for upskilling BTech and master students on the VLSI design aspect. Okay, so you can maybe look at the website and you get more details on this. Okay, thank you.
Good morning, all. Welcome to you all to the final day of our workshop. And today we'll start our program with a talk by Dr. Krishnakanth Avalur. And I'm happy to introduce Dr. Krishnakanth Garu to you all. Dr. Krishnakanth is a founder and a CTO of MOSart Labs, a VLSI edutech company founded for upskilling EC and EEE students in the field of semiconductor technology and chip design. He served as Director of Analog Mixed Signal R&D at AMS Semiconductors. He is an IEEE senior member and currently the Vice Chair of IEEE CAS EDS Joint Chapter, Hyderabad, and is frequently involved in delivering technical lectures at various universities. He received his PhD from IIIT Hyderabad. He finished his BTech and MTech from IIT Bombay with specialization in microelectronics. He was awarded President of India Shankar Dayal Sharma Gold Medal and IIT Bombay Student Roll of Honor in 2002. Analog IC design is his passion, and his specialization includes sensors and sensor interfaces, high performance analog signal processing, power management, and sensor interface for automotive and consumer semiconductor IC design. He worked earlier with Texas Instruments Bangalore and Qualcomm Logic Hyderabad, leading the analog IC design teams. He is an adjunct professor at IIT Hyderabad and Digital University, Kerala. He is an academic council and BOS member at several universities, and he has 13 patents and 11 IEEE publications to his credit. He is an associate editor for TCAS2 for 2014 and 2024 and 2025. We are glad to have you with us today, sir. A warm welcome to you, and over to you, sir.
So good morning, everyone. Glad to be here, and thank you for the introduction, ma'am. The topic for my lecture is going to be on CMOS power management integrated circuits for automotive applications. You know, I always like to start from application perspective whenever I take a lecture. You know, really we want to understand why we need to learn about this. So if you have seen one of the core R&D sectors that Indian Semiconductor Mission has identified, it is on automobiles, electric vehicles, energy efficiency. It's a very core, fundamental area that is going to see a lot of traction across the world, and certainly Indian Semiconductor Mission is also keenly focusing on this. There are several projects that are being run in this area, and with this advent of these electric vehicles, you would have seen so many electric vehicles now that are there. More electrification, having EV cars, autonomous three-wheelers. So all of these you'd see this traction coming in the next 5 to 10 years. You'd see lots and lots of these EV vehicles. So it's important to understand how these semiconductors, as circuit designers or electronic designers, what is it that, and what are the challenges in this domain? To redesign something for an automotive application, what are the challenges, what are the design constraints, what are some of the aspects of this power management circuit. So this is the scope of my talk today. And as always, I don't want to be one-way communication, so please feel free to interrupt me or raise your hand, and then let's have more interactive session. Right? So a typical, PMIC means Power Management Integrated Circuits. So this is a short form that is typically used for when you're talking about power management circuits, especially at a VLSI as an integrated chip. So what are the typical power management IC requirements? So when you have to put something in a car, right? What does the environment look like when a chip is inside a car? So it's something very important to understand, because this is what is defining a lot of things. The choice of our process technology, the choice of our architectures, a lot of it is dependent on what the application is, what the environment is. Okay. So now, to start with, if you look at any a typical, which is charging. So when fully charged, the car battery is about 14 volts, and this can go when almost about to discharge. This can go as low as 8 volts, 7 volts, and then so on. So the integrated circuits, what you're designing for, are going to see the supply in a car is going to be anywhere from, let's say, 6 volts to 18 volts, right? And if you're talking about touchscreen controllers, if you're talking about Bluetooth connectivity inside a car, you're talking about capacitive sensors, you're talking about graphic processors, microcontrollers putting inside a car, right? And we all know, like a typical 8051 controller or 8085 controller or any simple IC, they need 1.8 volt or a 3.3 volt or a 5 volt. But here we have a huge 14 volt battery, right? So obviously this means that each application or each piece of hardware, whatever the supply voltage is needed, you have to down convert it. So from the energy source, which is your battery, you have to do an efficient power conversion to the voltage that you want. So that's where this power management ICs come into play, which are really giving you or delivering an efficient power at the required voltage that you want to run your circuits on. Right? And so in some cases, when you have load dump, you can see transients as high as 42 volts. And the output voltage typically you want is anywhere from 1 volt for graphic processors, or for olden microcontrollers, you still need about 5 volts. Some motor drives or gate drives, you still need it. And this is the range of output voltage that you need. And the power management circuits that are they need to supply at least a 50 milliamp load current for the application to anywhere between 5 amperes. So it's very large. So here we are not talking about the electrification. EVs, you really need even hundreds of amperes. For a motor driver AC, you probably need 100 amperes. Here we are limiting the scope to few amperes because this kind of caters most applications. Then the temperature range that you see inside a car, especially the ICC, is about anywhere between -40 to 150. Why? That's because most of the circuits we are talking about are power management circuits, which will have their own self-heating. When you're delivering a load, right, you're going to also have self-heating, which will increase the temperature. And if you're designing a circuit that is in your dashboard, maybe 85 degrees C is probably maximum. But if you're designing something that is close to engine controller, right, engine is going to be really, really hot. So the ambient temperature that the ICC is going to be 125 or sometimes 130, 140, and you add self-heating, it will even go to 150 degrees centigrade. What this means is that the circuits that we design as part of automotive applications needs to withstand -40 to 150 degrees centigrade extended temperature range. The first challenge in automotive. So second challenge, first is the voltage range, second is the temperature range. And in some cases you need an extended temperature that needs to go as high as 175 degrees centigrade. Really bare die. We also do a bare silicon die with a lot of heat sinks there, and the transistors or some of the circuits needs to withstand 175 degrees centigrade. So it becomes a challenging, it becomes a big challenge to really design circuits to meet a reasonable performance. Of course, as an automotive requirement, you also have automotive protocols, data protocols like LIN, CAN, FlexRay. Some of these are data slightly low baud rate protocols, and they have their own standards, emission standards. When I say emission standards, like if you sit in an aeroplane, right, as soon as the flight takes off, air hostess will tell you, please shut off the mobile phones, because why is it so? Why are you asked to turn off your mobile phones or laptops when it is taking off or landing? Yes? Signal interference, electromagnetic emissions. There is going to be critical control that happens between your front cockpit and also the engines and so on. So, and this electromagnetic interference, we don't want this to create any trouble. And this is like a mandatory requirement across the world, and nothing different here. Though in smaller size, the EM emissions in the car, there is a certain standard in terms of the data. Because as an example, let's say you have an airbag deployment, right? If you're designing circuits in a consumer mobile phone, right? Let's say it doesn't charge properly or the touchscreen is not responding, it still is not considered as a hazard. It's not a human hazard. Okay, worst case, you will throw the phone. You will not be happy, but you will buy a new one. But imagine you're talking about an airbag deployment inside a car. So this needs to be an accelerometer sensor that should detect, and it's not like you will deploy airbag every day, right? It's probably happens once in a lifetime, but that sensor needs to be ready throughout for whatever lifetime of your car. So, and it needs to be reliable, it needs to be responsive at that particular temperature and so on. So this is what makes the automotive applications more challenging to design. Then of course we have ESD requirements, a very, very stringent ESD requirements, 8 kilovolt HBM. These are the, I mean, typically if you know ESD numbers, consumer applications have 2 kilovolt ESD, which needs to withstand typically, but in this case you need 8 kilovolts and sometimes even 12 or 6 kilovolt system ESD, very, very stringent ESD requirements for the chip. Then you have electromagnetic compatibility requirements, and then because automotive needs safety to be incorporated into design, there are issues in terms of design for test, manufacturability, quality. How often do we change our mobile phones? Yeah, how often do you change your mobile phones? 3, somebody like me 5, 6 years. And how often do you change your cars? 7, 8, 9, 10, whatever, right? So this means same circuit, same LDO, same sensor, whether you're putting in a mobile phone or whether you're putting in a car or if you're putting in a spaceship, right? The reliability requirements are completely different because the lifetime requirements are different. So this sensor or the power management ASIC should withstand 15 years of lifetime, at least guaranteed performance within a certain limit for 15 years. And we don't have time machine. How do you guarantee that the circuit that is designed at t equal to 0 today works reliable for next 15 years? Right? That's a big challenge. So that is where the concept of design for reliability comes into play. And like as engineering students, we all have experienced this. We can always go back to a professor and then say, sir, it was working yesterday, it's not working today, and we don't know why. Okay? And you don't have an option here. Your circuits have to work reliably and with high quality. And in addition, there needs to be a lot of protection that needs to be in place: thermal shutdown, over voltage protection, brownout, over current protection, and suddenly there are brilliant people who just connect the battery in opposite side. Okay, this just means that instead of giving a 14 volt, you give a minus 14 volt to your circuit, and of course that should not damage. And in that condition, when you do a jump start with this cable, so you literally abuse your battery, right? You abuse it, and all this, so the circuit needs to withstand all this abuse, if I can say that, right? And that's exactly what the design challenge is when you design any circuits in a automotive electronics domain. And extremely high quality. You need Six Sigma designs, really, which means 1 in, let's say, 10 million should be allowed to fail, nothing less than that. Okay, so now let's understand about battery before we get into the circuits, right? Maybe you can turn off this light so that it's probably visible to others. Slide. Yeah. Very good. Okay, so let me talk through it while we get the slide there, right? Okay, automotive battery. So when you have, see, your automotive battery is about 14 volts. Never mind, these things happen, don't worry. Okay. So automotive battery is 14 volts. Now, when you do engine cranking, when you start your battery, right, you can have the load transients as high as 50 volts. When you do a reverse protection, or when you're talking about some scenarios, right, your voltage can be really, really high. I think I'm still not seeing it. Okay, let's do it this way. So what are the transients you see on a 14 volt battery? Now, in case of a load dump or a failed voltage regulator, inductive load switching, ignition pulse, harness coupling, ESD. So these are typically the scenarios that happen in a car. Now you can see that the 14 volt battery, which we think is a fixed voltage, which we are used to, right? It's really not fixed, and something happened to this. Okay, so you have your voltage levels of a 14 volt battery can go as high as 125 volts, 18 volts, in this case, inductive load switching. So when you turn on your AC, right, this can go to 300 volts for a very short time and then come back minus 40 volts and so on. So we'll all be surprised, how come a 14 volt battery from all perspective, it's just 14 volts, which is nicely sitting somewhere. He's seeing this level of voltages. It's a very, very harsh environment. That's the point I am trying to make. And each of these voltages have a certain time duration, or these events have a certain time duration. So there needs to be lot of external protection that needs to be put in place before you can actually build anything in a VLSI or in a CMOS, because the voltages are going to be pretty high there. So here we are talking about circuits where we have protection, and we want to limit the circuits which can withstand a voltage of 50 volt, right? So the chip, whatever we are designing, the maximum voltage we want it to be limited to 42 or 50 volts. Functionally, it will still be 6 volts to 18 volts. So this is the boundary under which we are designing an IC. Anything more than 50 volts or some of these transients, right, like a 300 volts, you cannot design reliably with these kind of voltages in an integrated scenario. So you need external protection. You have transient voltage suppressors on the cable harness which will protect this IC externally, but the scope of our talk is going to be on, when I say high voltage, it's going to be maximum 50 volts. Okay, so what are the variations? So now we talked about battery. What is the variations we typically see in an integrated circuit environment when we design a chip, an integrated circuit in an automotive environment? What are the challenges? First one is the environment. Voltage, temperature, EMC, ESD, all these things can change. And why it changes? Typically because the VDD needs to be, VDD you always have a variation. There's going to be noise because of the load. So there is never a clean, stable voltage supply. It's always a noisy supply. Every practical scenario, it's a noisy supply. There is no clean current or clean supply in the world. It's all about what is the tolerable ripple that you can have, what is the tolerable noise. And then there is ambient temperature based on whether it's in a dashboard or whether it's close to the engine, and then the on-die temperature gets elevated because of a chip power consumption. I'll talk about this a little later in my slides. And based on the operating temperature, whatever you want to do, we can now pick, if it's a commercial application, a smartphone maybe 0 to 60 C, industrial minus 40 to 100, military applications you need minus 50 to even 125 C, and some applications you really have to go to SOI CMOS, minus 50 to even all the way till 300 degrees centigrade. So for our scope, we are limiting to a high voltage CMOS process which can withstand 50 volts. Now, second topic is a very important topic which we are somehow not aware, but a big issue for industry, whoever is designing. Second is a wear out. So do circuits age like human beings? Like we all age, right? So do circuits age? Yes? Yeah, so obviously, when you buy a new phone, great battery life, touchscreen is excellent, you are really fascinated by this gadget. 2 years later, battery is not charging as nicely as you want it to be, the touchscreen is not so responsive. Clearly we know circuit is aging, right? And it's real, and it happens because of practical phenomena. The aging of transistors are because of hot carrier injection effects, negative bias temperature instability, time dependent dielectric breakdown. All of this cause threshold voltage change of the transistors, MOS transistors. So when I say threshold voltage, it just means that the voltage that you need after which the transistor is turning on fully. And this plays a big role in terms of the analog performance or the timing. All of this plays a big role. And so now considering that the transistors are aging, right, what do we do? How do we estimate the performance of the device 15 years later? Because you have to guarantee a lifetime. You're designing today, you're testing in the lab, everything is working fine. Now how do you know this same circuit works 15 years later? What do you do? This is where the concept of reliability comes into play. Now, if you go to a cardiologist, right, they put you on something called treadmill test. How many of you have seen that? Treadmill test. So it's like a treadmill, and they kind of stitch electrodes all around your body, and they ask you to run. Okay? And while you are running, the ECGs are recorded, the signals are recorded in a machine which is now sensing how your heart rate is responding to a stress as you kind of increase the speed of your treadmill. And then they'll keep increasing the speed to the point where you say, no, stop, I can't run anymore. And then they will see how your heart is recovering back from the stress. Okay? And now looking at the reports, doctor will tell you, boss, your cholesterol level is high, you better do daily walking or whatever, right? So how are they estimating the lifetime? you are subjecting something to stress, you're looking at the performance of that during a stress, and then you're estimating back what would be the lifetime. Apply the same logic to your circuit. If your circuit operates at 3.3 volt and the circuit is operating at 0 to 60 degrees C, I can put the device at 125 degrees C at a slightly higher voltage and then estimate how long will the circuit survive this extended stress. And now there are models that are built in to say, if my circuit withstands 125 degrees C for let's say 1000 hours, which is reasonable, 1000 hours is about 43 days, then the circuit will withstand 60 degrees C for 1 million hours. This is, Arrhenius equation. That's what Arrhenius equation is all about. And this is the whole concept of reliability. You do a stressing. There are several tests, high temperature operating life test. You can do high temperature head stall, HAST, all of these, power temperature cycling, all of this to understand the performance of the circuit during stress, and then you interpolate back and say, okay, I will guarantee 15 years of my lifetime. The circuit will work with a reasonable performance. 2, as circuit designers, what we also use is called aging models. So this means when you look at a single transistor, right, and you have a set of SPICE models where you have your thresholds, you have your mobility of your NMOS, PMOS transistor, all of this, dielectric constants on. So then using these models, you kind of tweak back the models and then say, what if after 10 years, the threshold voltage has increased, the mobility has reduced, right? So you now create a aging SPICE netlist model. You simulate the circuit with this aging model also to see or to estimate back the performance that you would effectively see 15 years down the line when the device actually degenerates. And this is what needs to be done to only guarantee the performance. So we need accelerated life tests to really understand how the circuit will behave 15 years later. So in short, nothing is constant in an integrated circuit. In a VLSI world, nothing is constant in absolute terms. What is nice thing is there are two transistors under similar conditions behave similarly. So the matching of transistors is what we use fundamentally to start building circuits. Okay, so when I come to the power management ICs, since this is the scope of the talk, what are the fundamental power management ICs and how do we, where are all we using it? First is the source of power. Source of power in an automotive side can be a lead acid battery, which we're used to, or a lithium ion battery. So you also see all the EVs now have lithium ion battery stacks, which can go to 300 volts or 600 volts. And then in addition to this, now there are other fancy, I would say, sources of power like solar, wind, thermal, vibrations, which are primarily related to energy harvesting. This has still not come inside your car. Solar, yes, some fancy gadgets have solar panels on top of your car where you still do something, but the energy you generate versus the cost. For a car, you demand a lot of energy. So mobile phones or some smart gadgets, it's still okay, but in terms of an automobile, this is still not enough. The energy efficiencies are not enough. So you don't find so much of this, but just be aware that some of these energy harvestings are still available in consumer products, would eventually, once the efficiency improves, would probably start getting into your car as well. So it could be, people are thinking of a solar paint of your entire body, of your car. So this means, if you are keeping the car in the sun, right, idle, so you should keep charging your battery. So those are some fancy things that people are looking into. Okay, once we have a source of power, then we need RF energy harvesters. You need something to really convert the RF energy into or rectify it, and you can do it with on-chip transformers or rectifiers, which will convert your AC energy into some kind of a DC voltage. Then once you convert here, we also need to ensure that we have a good power efficiency, and this is where we look into circuits which have maximum power band transfer. This also means that you are making sure that you are delivering the load current at the best efficiency of your system. And why is efficiency important? Efficiency is simply related to what is the input power, V into I, of your system from the battery that you're taking versus what is the load that you're delivering, output power, which is V out into I out. Now, ideally you want the output power to be same as your input power, and whatever is the loss that you see is related to the efficiency and so on. So you can have, for efficient circuits, you can have DC-DC converters, and some of these variants like buck boost or SEPIC, You have all of these are different topologies that are related to the DC-DC switching converters. You can have CMOS converters, which are single inductor, multiple output. This is related to reducing the number of components, and you can, with one external inductor, how can you deliver multiple outputs? And then you have MIMO converters, and and of course all of these are different power converters that are used. Each of these, though they are transferring energy efficiently, because these are hard switching devices, they have a lot of output noise. And because of this, you also need some way to clean up the power, and typically this is done by a low dropout regulator. And you can have a lot of varieties in terms of wide band, on chip, or ultra low power, low LDOs, low dropout regulators. Okay, and in addition, you can, related to the IPs, you also have the choice of process technology, CMOS or a high voltage CMOS, a BCD, a gallium nitride, silicon carbide, off chip or on chip, based on what voltage and what power range you are targeting. So these are, I would say, a whole recipe of, a whole menu of things where you typically come across in a power management IC. Now, so to now design, let's come back to the topic of designing something which is working at 50 volts, right? To make an integrated circuit that is working at 50 volts, you will need a process, the transistor technology that supports this voltage. And if you look at power management IC operating range, right? For a 14 volt battery, the functional requirements mostly are between 6 volts to 18 volts. And then you have external transient voltage suppressors between 18 volts to 42 volts. And the transistor that you're using should withstand 50 volts for the lifetime. And then in terms of ESD, which is a small time duration, it should withstand ESD pulses as high as 60 volts. And the transistor breakdowns typically happens at 65 or beyond. So now you look at it, to make your circuit operate at 14 volts, you really are forced to pick a transistor whose breakdown is 65. You cannot go any lower, simply because you have to live with all of these requirements, right? And that sets a first challenge in terms of your transistor performance. Higher the breakdown voltage, higher is your R-on, the on resistance, and higher the R-on, lower is the efficiency, because I square R loss, I square into R. So to deliver the same current, if you have a higher R-on of your transistor, you have higher loss, higher conduction losses. So that's the thing that we need to remember when we're designing some circuits in a given range. I think we covered this. If the ECU or the electronic control unit is under the dashboard, then the operating temperature is, let's say, -30 to 85. In the engine, it can go to 105 or 150, or sometimes when it is connected to the engine, it can also be as high as 175 degrees centigrade. This is a temperature that the IC should withstand in the automotive application based on where it is placed. Okay, let's take an example of a simple example of a reverse camera power management IC. And one of the things that we need to understand as circuit designers is about the thermal calculation here. So how does the temperature impact my design? Okay. So let's assume we have a DC-DC converter that's coming from a battery, which is delivering output voltage around 5 volt here, and at 5 volts we have 3 LDOs that are connected. You need to supply 5 volts to something, then you need a 3.3 volt, you need 2.5 volts and 1.8 volts. These are the 3 different voltages. It could be for a microcontroller or a graphic processor, or it could be for a motor driver, or it could be one of the bus protocols, right? So this is a typical application that a reverse camera PMIC would see. Now, if I look at, even before looking into the architecture, right? If I start looking into what does this mean in terms of my temperature, right? You would see that when I do a thermal calculation, I think some of the slide is, yeah, okay, it's good. So I think it's not showing up fully, but you can start doing a simple calculation saying, okay, what is the DC-DC load current? It is 150 here, 150, 150. So all the 3 LDOs consume, because for LDO, the load current is almost equal to the input current, right? The quiescent current is usually small. So if the LDO is delivering 150 milliampere, you need at least 150 at the input side. So if you add up all of these numbers, plus another 150 delivered directly at 5 volts, you will see that the DC-DC needs to supply 600 milliampere here at 5 volt. So 5 volt and 600 milliampere is your load requirement for a DC-DC converter. And that would mean you have a certain power dissipation, and based on the experience, when you can look at converter efficiencies of, let's say, 85 to 90%, you will realize that, I think the number is not very clear, but if you just do this math, 5 volt into 600 milliampere, which is the output load, divided by an 85% efficiency, you would end up with power dissipation inside the DC-DC. The self dissipation here is roughly around 0.5 watt. So this is the wastage just to deliver 5 volt and 600 milliampere from the DC-DC converter. For an LDO, it is simple. You know, the self dissipation of LDO is simply the dropout, which is 5 volt minus 3.3 into 150, 5 volt minus 2.5 into 150, 5 volt minus 1.8 into 150. Right? If you add all of these, you end up with a total power dissipation. This is the wastage of this chip based on your circuit efficiency. This can be as high as 1.6 watts here. And now, when this means when the circuit is sitting in a PCB, in addition to delivering the load current you want, this is dissipating a heat which is equivalent to 1.6 watts. And each of these have a certain thermal coefficient, thermal constant or thermal resistance to the package. And as an example, if your thermal resistance is 30 degrees centigrade per watt, so this means for every 1 watt you dissipate on the chip temperature increases by 30 degrees centigrade. That's called as a thermal resistance. Now here we have close to 1.6 watts. So this means the junction temperature, maximum junction temperature you can handle is 150 only from the SPICE model. So the maximum ambient temperature, which means what is the application temperature, this can only be 92 degrees centigrade. What this means is that if the maximum ambient is 192 degrees centigrade, if I add my self-heating of the circuit, I am going to touch the limit of 150 degrees centigrade already, at which my SPICE models are qualified only at that. Now transistor models are typically qualified only at 150 degrees centigrade. So this application I cannot use more than 92 degrees centigrade. So that is already telling me by a simple math that if I have to design a circuit like this, I cannot put it close to the engine because the circuits will fail. I can only use this in a dash box application. Where the ambient temperatures is less than 85. Now, regarding the process, you can see that this is a standard 3.3 or 5 volt technology process where you have, let's say this is your substrate and you have an NMOS transistor which is in a P tub, and then you have the PMOS transistor in an N tub, and you have the poly, R poly all connected, and you can see that the bulk source drain connection are here, and then you also have these metal connections, different metals that go all the way to the top. Now, when you want to do something in automotive, you need isolated transistors because you have to withstand higher voltages. And for isolated transistors, you want the transistors to be in its own well. So, an NMOS transistor would be in its own RP tub, and a PMOS transistor would be in a shallow N tub. Both these put in a deep N well. This is called deep N tub, and then which is built inside your standard P substrate. You can now see that just the construction of these transistors, because you want isolated transistors which can withstand higher voltage, this is now increasing the complexity of the process itself. And this is about still a low voltage. Now, if I want to extend this to a transistor which can withstand 50 volts, how does a transistor look like? So you can now, let's just look in the bottom part just to be clear. So you can see that this is a drain. Okay, it's an NMOS transistor. You have a drain, and then you have a huge oxide, field oxide here, and this is your gate. So your gate is now all wrapped around this field oxide, and this is it's an extended drain, and what this extended drain is doing is now it is dropping the voltage across this drain junction. So that is where the transistor is able to hold on 50 volts. It's mainly across the drain junction. The VDS, the drain to source voltage, you are able to manage 50 volts there simply because you have now an extended drain where you're dropping. It's not very efficient because you are extending the drain. It adds a lot of drain resistance, but this is the only way to drop this additional voltage and really build high voltage CMOS transistors. So anyway, you have the RP tub here and all of this in a deep N well, the source, gate, drain, and the bulk all in a deep N well. And then for bipolars you need a vert N1, so you can also see that you have an RP tub, DN tub, and also a N connected here, and you can have also vertical bipolar transistor. This you need typically you need bipolars for band gaps or some high-end ESD structures, right? So you can now see not only design, but the process technology is now becoming more complex from a standard CMOS that we know to a more high voltage CMOS which can withstand these voltages. Okay, so some latest trends in this transistor is that the people have, because based on the application we really have to tweak the process. If you really want to design only for 10 volts, right? We don't want to use the same 60 volt technology to design something at 10 volts. So you have to tweak the process so that your breakdown voltage can be made smaller, drain extension can be made smaller, so that the transistor has better on resistance, so that it can be more efficient. And as an example, an optimized 60 volt transistor is 22% less area compared to a standard 120 volt NMOS transistor. So this plays a huge role when we are talking about power management circuits, because ultimately the silicon area, the amount of area you spend, is not only related to your the size, but also related to your cost. Okay, so this is a case study of a rear view camera PMIC. So we were looking into building a rear view camera application, and the existing PMICs from Freescale, all these devices, one of them were bulky with all individual ICs, and the second one was only a 5 volt input supply, so we cannot integrate from a lead acid battery, because battery is 14 volts, and TIs, they are all linear regulators and they are not power efficient to deliver higher currents, right? So, and when we looked into some literature on the hybrid regulator based PMICs, hybrid regulator is essentially a combination of DC-DC cascaded to an LDO. So efficient DC-DC, which is converting a higher voltage to low voltage, and then a LDO cascaded to it, which is cleaning up your DC-DC noise. So you get a final clean supply there. So they have their own limitations. So what we thought was, okay, what are the problems here? One, you have bulky external components, which means more space, more weight and higher cost, and we kind of need multiple integrated circuits for each voltage, or we have circuits which are optimized for highest load current only. So only the peak load current your efficiency is good, but then most times, let's say you're supplying a microcontroller, the peak requirement of a microcontroller is 1 ampere at the peak clock speed. But then most times the microcontroller is not in that mode, it's probably in the intermediate medium range only. So it is important that when you build circuits, it should have good efficiencies across the entire load range. Then your system will be more efficient. And some of these, they don't cater to 150 requirement. Like we just mentioned, we with the self heating, you would end up with 150 degrees centigrade, right? So that was the fundamental problems. And we said, okay, let's now do a systematic study of automotive hybrid regulators in terms of a design, layout and packaging. This was a good research problem to start with. Okay. So what was the motivation to go for this? The driving assistance systems, which are called ADAS, right? Advanced Driving Assistance Systems. US has made it mandatory that every car as part of ADAS should have a reverse camera. Now you see this is now almost in every car here, every car that is available, there is a reverse camera, and which is transmitting data. So you need a power management system to take care of this reverse camera. So when we tried nailing down the applications, right, it looked like you have the input voltage is from 6 volt to 18 volts, and then you need three voltages at 150 milliampere load, 1.8 volt, 2.8 and 3.3 from this supply, and we need one more output which is 1 volt to 1 ampere, 1 volt 1 ampere. Ambient temperature is 105, junction temperature cannot be more than 150 because of SPICE models, and the cost need to be minimized, the efficiency need to be more than 60%. So this is a target requirement. This is more a requirement. And when you're working on a research problem like this, especially if you are a master's student or a PhD scholar, right, this is very important step. So really list down your boundary condition. What exactly are your conditions that you need to design? Don't start with a very generic problem and say, I will design the world's best circuit. It never happens that way. You have to trade off something. You should always be clear on what is the key consideration in your application and then optimize for that. So in terms of diagram, you need this. We wanted to design this power management unit, which was giving the 3 voltages and was able to take the supply from 6 volts to 18 volts. Okay. So now, and of course, when you do a simulation, you also have to consider always, CMOS side, you need the typical process, verse speed, verse power, verse zero, all these corners, resistors, you have corners, capacitor, bipolar, all of these are necessary to be simulated for where you guarantee the design robustness. So we wanted to let's come up with a strategy of how do we design. So this should also be clear. How do we design this? What is the strategy we go about? One was to see that we want lesser number of discrete components. So the strategy would be to integrate as many LDOs and DC-DCs into one single chip. Obviously, more integration, lesser is the weight, better is the reliability. You know, there is also a big concept of reliability in automotive where you say more number of components you solder on the board, right? The higher the chances of failure, because let's say every component has to have 1% probability of failure, and you have 10 different components, capacitors, ICs, all of them soldered, right? The probability of failure is now much worse because there is a probability of each one failing. So the probability of, I mean, it's a simple math. If you say probability of one component failure is 1%, right? This means the probability of the component working is 0.99 and another one working is 0.99, another one working 0.99. Now you look at, do all the multiplication, you would end up with the probability of the application working is 0.9, which is 10%. So there is a 10% failure when you have all the different components, let's say 10 different components, each having a probability of failure of 1%, right? So it's not good. You don't want 10% failure in your automotive applications, not if this is deploying an airbag, right? And that's why it is important to make sure that the more you integrate it, that's also a motivation for integration in automotive. The more you integrate, you're now making it more reliable. You have lesser number of components, lesser probability of failure, and that's one of the motivation to integrate some of this. That's where the reliable solution comes in. Robust design to survive harsh environment, and of course we need good efficiency when the camera is on, when the PMIC is full load, or when the camera is off. Okay, so now the strategy was to see, okay, we can now build a high voltage DC-DC, we call it as HV DC-DC, which is supplying from a high voltage. When I call it high, it is greater than 5 volts to about intermediate voltage, like 5 volts. Or we can do a high voltage DC-DC with moderate step down ratio, where you can get efficiencies of 85%, or a low voltage DC-DC where your supply is 3 volt to 5.5 when you take it to a lower voltage, right? It's a low voltage to low voltage. The efficiencies can be really 90%. So you can see that based on the type of DC-DC you choose, based on the step down ratio. So step down ratio is simply the ratio of your output to your input voltage. Like, if you have 12 volts input and a 1 volt output, you have a very high step down ratio. If you have a 12 volt input and a 5 volt output, it's not so bad. So you can get better efficiencies in DC-DC converters if your output is 5 volts than compared to 1 volt. So this is something that you should also keep in mind when you review research papers to understand or to benchmark whether one efficiency or one LDO or DC-DC is better than the other one. You should also note down at what output voltage are they talking about efficiency, right? And then you can do an apples to apples comparison. So fundamental properties of these two blocks, DC-DC switching regulator, it has much better efficiency, but the output triple is high because this is a hard switching device. Then there are a lot of external components like inductors, capacitors, Schottky. You can't integrate them on the chip with the value of inductors we are picking. So these are external components on the PCB. So more failure rate and also more bulky. So the whole application is going to be more bulky and more expensive. And silicon area typically high because the power transistor is switching from 0 to, you're completely turning on or turning off. For an LDO, it's nice, the efficiency is poor, but the output triple is negligible, it's clean, you just need one capacitor, or in some cases you don't even need this capacitor, can also be integrated on the chip. And the silicon area is low because you are regulating linearly the pass transistor. Okay, so each one has its own advantage, and the smart way is to see how we can use a combination of these to build the application. So we started with the PMOS architecture choices. We said, okay, let's now take the best efficiency in the world, right? So 12 volts to 2.5, I need all 4 high voltage DC-DCs, which is giving you all of these. And then another option was to say, okay, let's not take all high voltage DC-DC because this is a lot of CMOS area. Let's take one high voltage DC-DC that is converting into an intermediate voltage of 2.9 volt. And then from this 2.9, I now use low voltage DC-DCs, which means the 3.3 or 5 volt transistors to give you the respective voltage. Like, it was looking good, the efficiency was really nice, but then you look at the number of DC-DCs here, they're insane, 5 DC-DCs, 5 external components, capacitors, a lot of noise in the system. It's still not a clean power supply. Then we said, okay, we want to clean up the power supply. Let's just add LDOs here. And because I want to add the LDO, if the output needs to be 1.4, then I need to account for a dropout of the LDO as well. So dropout is the fixed voltage drop that you see on the LDO pass transistor during a regulation. So if I had to give a 1.4 volt here, the DC-DC need to be given 1.7 volt. So if I need 2.5, we need a 2.8 here. And now the instead of 2.8, so here you could see 2.5 to 2.4, now it's becoming 2.8 to 3.2. So the voltages are now going up. So more components, though the supply is cleaner now, but then you still have more components, and then the efficiency is getting poorer. Then another option is to see, okay, why not apply the same logic what we did on high voltage DC-DC to low voltage DC-DCs, and then say I will put one high voltage DC-DC, then run all the 3 LDOs with one low voltage DC-DC only. So this means you have one LV DC-DC connecting at the highest voltage of 2.8, and then this is supplying all the 3 LDOs. Similarly, I am going to have one dedicated LV DC-DC for the second one, which is supplying 1.4 and 1 ampere. And the reason why we have split this way is because if you see here, this low voltage DC-DC has about 600 milliampere, 150 plus 150 plus 150, and this is 1 ampere. So it's better to split it, to do a partitioning in this way, so that you almost have similar range of currents in the both LV DC-DCs. Going a step further, when we do a calculation here, we realize that the ambient temperature, go back with the thermal calculation. If you go back to the Excel that I showed first, right? When you do a thermal calculation, you will realize that you cannot meet the temperature requirement if you have everything on one single chip. So the smart way was to say, okay, let me build 2 different ICs here. Now I will split into 2 ICs. One IC that is targeting a high voltage DC-DC and 3 LDOs, and a second IC that is giving one high voltage DC-DC and a single LDO. So it's a 2-chip solution, right? Which will now meet the efficiency, output ripple, cost, and also the ambient temperature requirement. So this is how we have started from a problem and then came down to our architecture choices. Now, when you do a comparison of these architecture choices in terms of you go back to the same Excel that I showed earlier. Now, if you do a temperature calculation, you would realize that for this last option that I showed, you can withstand a temperature of 118 and 125 at the junction. Everything else was much higher because we were integrating more and more into the chip. A lot of these details are available. I mean, we have also published a paper which I'll show later. You can go into that. And as a qualitative summary, you can see that this type of PMIC architecture partitioning was giving you low output noise, moderate efficiency, low external components, which is good for cost and reliability, low junction temperature, this is good for our SPICE modeling, and moderate cost and moderate PCB size. So this was our trade-off in terms of the architecture that we have chosen for this. And subsequently, I am going to focus only on the PMIC 1, which is talking about one high voltage DC-DC and 3 LDOs. So the proposed 2-chip solution was actually looking like this. Now we have this high voltage DC-DC which has 3 LDOs and another high voltage DC-DC with 1 LDO with 1 ampere. And yeah, you can see that this was supplying to a sensor GPU here, and this was supplying to a microcontroller.